of having the molecule and ask you to rationalize what the spectrum looks like, we're saying now we give you the spectrum and you try to work out what does the molecule look like. So that's our goal of today. Before we do that, we want to quickly go over two of the leftover topic. The first one being degree of unsaturation, and the second one being carbon NMR, and also some of the 2D NMR. And at the end, we'll do two examples together in how to use all kinds of spectroscopy method to get idea about what an unknown species looks like. So, before we get started, as a quick review, we have covered three of the major spectroscopy methods. The first one being proton NMR. That's saying on proton NMR, we have 4 different types of information you can get. Number of peaks, that's telling you the chemical equivalence of your hydrogen atoms. And just keep in mind, one of the common misunderstanding of number of peaks and splitting pattern is the chemically equivalent hydrogens do not shield each other. So one of the good way to remember it is now imagine you have a benzene molecule. Now your benzene molecule have 6 hydrogens. And if you look at exact each of the hydrogen, you'll be like, oh, it must be a triplet. But instead, because all these hydrogens are chemically equivalent, they do not shield each other. So that's why this hydrogen are just singlet hydrogens. We have that kind of problem on your multiple choice problem. It's when you're having this kind of molecule. We're asking whether or not that is a singlet. And in this case, these two are equivalent to each other. So that's why they're all singlets. Nevertheless, using proton NMR, we can get information like how many types of hydrogens we have, what's the splitting pattern, or what's the chemical environment around it. And then by chemical shift, we know whether it's next to an electron withdrawing group. And also you can read the table to get information about the chemical shift. And by taking the integration, you're getting the ratio between different types of hydrogen in your molecule. So that's your proton NMR. And then last week, we spent some time going over IR, or infrared spectroscopy. So IR, the primary use is to use it to identify functional group, right? So in IR spectroscopy, remember the 2 iconic functional group we discussed. One is the OH group, or NH, OH, NH stretching. So these are going to be your broad peak around the 3200 region, right? So these are your 3000 region, 30 to 3200, depending on the exact group. The other is your sharp carbonyl group. That's around 1700. And whether or not we have these peaks, it tells you whether or not you have an OH group or a carbonyl group in your molecule. And then we spent some time talking about mass spectrometry. It's spectrometry. What we did is you break down your molecule into cations, into different cationic fragments. And by looking at the mass spectrometry, you get information about what's the mass of your molecule, what's the mass of different fragments. And those fragments are typically more stable when you're having more stable carbocation, right? So that's why we spend lots of time talking about the stability of the carbocation. So these are the 3 tools we have been introduced. And then one of the terms that we should have introduced before is the degree of unsaturation. So degree of unsaturation is not a hard term. This is just information that's hidden in your molecular formula. So if you think about it, now let's look at 1, 2, 3, 4, 5. We always have 5 carbons, and depending on how many double bonds you have, if you look at the molecular formula, if you write down the molecular formula, by write down how many carbon and hydrogen atoms are there in your molecule, you can find some kind of trend. So let's use the all saturated example, or the linear pentane. What we have is we have 5 carbon and we have 12 hydrogens. So that's 5 times 2 plus 2 for your all saturated linear pentane. Now, the second one comes is with 1 unsaturation. Now, with that 1 unsaturation, if you count the number of hydrogen, it now becomes 5 plus 2 plus 2 minus 2. So this minus 2 tells you we have 1 degree of unsaturation. Or we abbreviate that degree of unsaturation to be DOU. Likewise, if you have a diene, now in this case, that's an example of your conjugated diene. In this diene example, we have 5 carbon, so 5 times 2 plus 2, that's your reference point, and minus 4. So this 4 tells you we have 2 times 2, so 2 degrees of unsaturation. And that same rule applies to cyclic structures. Now, if we have only 1 ring structure, like a cyclopentane, this 1 ring structure is telling you, hey, this one has 1 degree of unsaturation. So we have 1 DOU. The relationship here is, if your carbon number is 5, then it's just 5 times 2 minus, plus 2 minus 2, so 1 degree of unsaturation. And then if your 2 rings fuse together, what we have is C5H8. So the 2 rings fused together corresponds to 2 degrees of unsaturation. All right, so that's just a general, so degree of unsaturation, just a kind of general rule people come out by looking at the molecular formula of different kind of molecules. Now we have the general formula to calculate our degree of unsaturation. It looks complicated, but here are just like number of atoms. Now your degree of unsaturation on the top, you have the 2 times the number of carbon atoms plus 2. So that's a number of hydrogen in your all saturated molecule, like in your pentane, linear pentane, plus the number of nitrogen in your molecule, minus the number of halogen, and then minus the number of hydrogen atoms. And in this calculation, you'll notice that oxygen and sulfur or your group 6 element are not part of your formula. So your group 6 element will not contribute to your calculation for the degree of unsaturation. All right? Now let's do some practice problems together. So let's do these problems in 2 different ways. The first way is I give you the molecular formula, and then I give you the molecular formula, and I ask you to calculate what is the degree of unsaturation. And I might ask you to give me an example in what does that molecule looks like. It doesn't need to be the same, but give me an example. So in this case, the molecule is C6H14. So if we calculate the DOU, that's on the top. We have the number of carbon times 2 plus 2 minus the number of hydrogen divided by 2. And that equals to 0. So the degree of unsaturation is 0. So when you're drawing the bond line formula, you can just simply give me any 6 carbon hydrocarbons without any double bond and also without any ring structures. So the linear molecule is correct. You can also have 1, 2, 3, 4, 5, 6. You can also have a branched molecule. So as long as you do not have a ring or a double bond in this drawing, they will have the correct degree of unsaturation. All right, so this is one way we can ask you a question. Now let's imagine a different way to ask you the question. Now imagine we have DOU equals to 1, and I'm telling you in this molecule, we have 1 carbon and 1 oxygen. Can you give me some sample molecule you can dream about that has 1 degree of unsaturation that contains 1 carbon and 1 oxygen? So this must be a double bonded like that. All right, so if you're calculating the level of unsaturation here, carbon here is just 1. 1 times 2 plus 2 minus 2 gives you 1 degree of unsaturation. So there are two different ways, well, several different ways we can ask you the same question, but don't remember the type of question you're expecting it. Try to understand just using that formula in different kind of ways. Now, the other way we can ask you the question is now we have benzene, or C6H6. And I can give you an extraordinary molecule like one of our benzene molecule we saw before. Let's say 1,2,3 hexatriene. Now that example we saw before, and can you point it out where that 4 degree of unsaturation comes from? So now if we look at this molecule, we can say we have 1, 2, 3, we have 3 double bonds and 1 ring structure. So overall, we have 4 degree of unsaturation, 3 from pi bond, and 1 from the ring structure. All right, so now when you're practicing this kind of problem, maybe you can dream about a different molecule, a still benzene. Can you rationalize where that degree of unsaturation comes from? Now, this is the same kind of isomer of benzene. Likewise, it also has 4 degree of unsaturation. So where that 4 degree of unsaturation comes from in this molecule. Right, so we have 2 from the double bond and 2 from the ring structure. So it's not a new concept. We're just using the concept from different perspective. So this is a quick introduction to degree of unsaturation. It's not hard. It's pretty straightforward, but practice on it and know how to approach this concept using different perspective. Any questions on degree of unsaturation? Okay, let's keep going. Second topic, carbon NMR. Oh, yes.
If you had like just a ring, like a carbon ring with no double bonds, that would still be 1 degree?
Yes, so 1 ring is 1 degree of unsaturation. Now you can have 2 rings fused together, right? Then you have 2 degrees of unsaturation.
Okay, thank you.
Yes.
Can you just go over writing that 4 again?
This one?
Like, did you do the math or did you just...
Well, you can do the math and get the same answer. So we have the 6 number of carbon, right? Times 2 plus 2 minus 6, which is hydrogen, and then divided by 2. Now, if you do that calculation on the top, we have, let's see, we have 1, 2, 3, 4, 12, 14, 8 divided by 2, that gives you 4. Okay. Next topic, carbon NMR. Now, in proton NMR, we know that in nuclear magnetic resonance, you get 4 different kind of information, right? You get number of peaks, chemical shift, integration, and splitting pattern. Carbon NMR is the same. Before we get into these type of information, for carbon NMR, the one take-home message is that carbon NMR is measuring the isotope of carbon-13 that is NMR active. So the majority of your carbon atoms are not NMR active, but carbon-13, which is one of the stable isotope of your carbon atom, is NMR active. Okay, so that's a little bit of the background. Now, in the carbon NMR, in all these 4 pieces of information, 2 of them are no longer useful in carbon NMR, at least in this 14C level. The first information, the number of peaks, or tells you the number of chemically non-equivalent carbon atoms. This part of the information is still relevant. By looking at how many peaks you have on your carbon NMR, it's telling you how many chemically non-equivalent carbon atoms you have. It's a very good hint in whether or not your molecule has symmetry. We'll see some examples on this really soon. Chemical shift tells you the environment of the carbon atom. Now, the environment of the carbon atom follows a similar trend, but a little bit more complicated. So I'm not going to go into any detailed trend of chemical shift. This one is rather you're just using the provided information in the table and then try to get chemical shift information for your carbon NMR. And then before we go into specific examples, the splitting pattern and integration are less important in carbon NMR for a good reason. So in your carbon NMR, your carbon-13 atoms are coupled not only by its nearby carbon-13 atom, but also by its hydrogen atom that's bonded to that carbon atom. So remember, your hydrogen proton is NMR active. Your carbon-13 is also NMR active. So now your proton can shield your carbon atom and causing a splitting pattern. But your neighboring carbon atom can also shield your carbon atom and creating a splitting pattern. This effect is not obvious in your proton NMR because after all, your carbon-13 is a very rare isotope. Now the result of that complicated shielding is you get this kind of very complicated splitting pattern. That's at the level of 14C, I do not expect you to understand or to rationalize this splitting pattern. Normally, in our carbon-13 NMR, what we'll do is we'll use the proton decoupled carbon-13 NMR. What does that mean? It means we're talking about no splitting pattern at all. Everything appears as singlet. And by doing that, we're actually removing some of the information, like integration, from those peaks. So your carbon-13 NMR in this class will always show up as all kinds of singlets, and we no longer talk about integration of those singlets. Now, we spent 5 minutes talking about that concept. But if you imagine this concept appears on your final exam, it might be a multiple choice question, right? It's why in your carbon-13 proton decoupled carbon-13 NMR, only singlets are shown. These are the concepts we're talking about. It's because the splitting pattern is complicated. That's why we only have singlets in your carbon-13 NMR. So these are typical things that we covered in class, but your mind might not have go in that direction. So this is, for example, it can be a short answer question or a multiple choice question and say why your carbon-13 NMR need to be proton decoupled. Just say. All right, so let's look at some of the other example questions on the carbon-13 NMR. Now, this question reads, again, this is a type of question. I give you the spectrum. I give you some candidates of your molecule. I also give you the molecular structure of these candidate molecules. And can you identify the most possible molecular structures? Now, how do we approach this problem? We read the problem first and get the information we can. Like we know the molecular formula here is C4H9Br. And we can calculate our DOU, the degree of unsaturation here. Doing that calculation, we have number of carbon times 2 minus the number of hydrogen minus the number of halogen, and then divided by 2. And what we have is, well, 0. So we're expecting 0 degree of unsaturation in this molecule by doing that quick calculation. Now, one of my candidates has a ring structure, so we're expecting the DOU equals to 1. So we can rule out this first one. And then we don't have to write out all the hydrogen and count them manually because these doesn't have any ring structure. These molecules doesn't have any double bonds. So we know their DOU is 0 and they are possible candidates. Now to distinguish these two possible candidates, we need to use our carbon-13 NMR. And now let's look at our carbon-13 NMR. It's proton decoupled carbon-13 NMR, so it is all singlet. Now we look at these singlet peak. How many peaks are there? Right, so the most important message we can get is the number of peaks of this molecule. Now if we look at it, we have a total of 4 peaks. This middle one looks promising. All my carbon are chemically inequivalent because their distance to your bromine substitution is different, right? So all of my carbon atoms on this molecule are chemically inequivalent. What about this molecule here? Why we're saying some of the carbon atom in this last molecule is equivalent? Now, if you think about it, this carbon here, it binds to bromine. It must be a different one comparing to this middle one. But now these two terminal carbons, they are chemically equivalent. Right, so the reason they're chemically equivalent, again, they're only binding to a single bond, is constantly undergo the free rotation of that single bond. So these two carbon atoms are chemically equivalent. So for this molecule, we're expecting a total of 3 signal in its carbon NMR. So that's why that one is not correct. All right. And let's do some more examples together. When we're talking about carbon NMR, it's a good way to identify symmetry in the molecule. We're just highlighting the possibility. Now, if we look at the number of peaks on your carbon NMR, and you count the number of carbon in your molecule, or in your molecular formula, it is a very good hint in whether or not you have symmetry in your molecule. So let's take this as an example. This might be a short answer problem. It's now I give you the molecular formula, I give you the carbon NMR, and I give you the molecular structure. Can you tell me which pairs of your carbon atom in your molecule are chemically equivalent? Or can you draw that plan of symmetry, making those carbon chemically equivalent? Right, so for this one, the best way to think about it is like we have 1, 2, 3, 4. So let's say if we cut it in the middle here, and we just think about these two parts. So these two parts are equivalent, these two are equivalent, these are equivalent, these are equivalent. Right, so this is one of it. This is one of it. The terminal one is one of it. And then these, all 4 of them, they're all equivalent to each other. All right, so the other way to put it is on top of that middle symmetry, you can also draw a second plan of symmetry, which explains why these 4 atoms are all equivalent to each other. So when we're talking about chemical equivalence, 2 take-home message. 1, we're talking about mirror plane, and 2, we're talking about free rotation over single bond. But that free rotation over single bond can be broke when you have a ring structure or when you have a double bond, right? So naturally, if you have a ring structure, it's a cyclic structure, then you do not have free rotation over the single bond anymore. Or if you have double bond, you do not have free rotation anymore. So that's this example here. Let's try that together on the right example here. So on this molecule, we have 1, 2, 3, 4, 5, 6. We have a total of 6 signals in your carbon NMR. So in this molecule, what we can do is draw this plan of symmetry in the middle. Now your OH doesn't have any carbon on it, but here you have the first carbon atom. And then these 2 are equivalent. These 2 are equivalent. This one is different. This one is different. And at the end, again, at the terminal, you have free rotation of those two terminal methyl group. So let's see, we have 1, 2, 3, 4, 5, 6, a total of 6 different kind of carbon atoms. Again, you have different, we have different ways we can ask you this kind of question, right? I can give you the molecule and ask you to predict how many chemically equivalent carbons are there, or consequently, how many peaks you expect to see on the carbon NMR. Yes?
Can you explain like how the 2 pink ones on the right are equivalent and the 2 orange ones, because the double bonds are like in different places?
Okay, 1 second. These two?
Yeah.
And what about these two?
No, of the other molecules.
These two?
Same stage, yeah.
Right, so the difference here is on the left-hand side and right-hand side, we both have ethyl group. So these two groups are the same. So that's why we can draw that second mirror plane that goes in between your atom. All right, so in this molecule, your OH group is different from an isopropyl group. So we only have one plane of symmetry. So that means these are no longer equivalent to each other. Right, so now imagine if we move this part into a different position, then your molecule don't have that symmetry anymore. It will have a different set of chemically equivalent molecules. All right, I'll probably post another Canvas assignment later tonight after I finish recording, and you can practice more on carbon NMR and also degree of unsaturation. Also IR and mass spec and everything. Okay, and then chemical shift. This one I'm not going to spend too much time on it. We'll just be going over and say, hey, you have the chemical shift table, and now you can get some information out of it. We're not going to focusing on the chemical shift for the carbon NMR for this lecture. Yes?
So for this chemical shift table and also for like the functional group table for the IR spectrum, would we like want to write all that down for the final?
I'll give you the table.
Okay.
Yeah, I'll post like an equation sheet. It's not a real equation sheet, but has all the spectroscopy table you'll need for your final exam. Okay, and before we move on, and I actually don't think I have time to finish doing our example together. I'll save that for next Monday. I don't want to rush anything. Let's spend some time look at 2D NMR. So 2D NMR, I'm not going to ask you to analyze any of these spectroscopy, any of these spectrum. But it is important to know that on top of the proton NMR and carbon-13 NMR we covered, there exists a possibility of coupling 2 different types of NMR spectrum together and getting yourself more information. All right, so just knowing these methods exist in the world of NMR spectroscopy. So they have really funny names, like COSY, that's correlation spectroscopy, or Hector nuclear correlation spectroscopy, or NOSY, nuclear overall Overherser effect spectroscopy. So if the fact of these spectroscopy method being 2D, just take home message is 2D NMR means we're coupling different types of NMR spectrum on the same spectrum diagram. Like if we take the COSY as an example, we'll look at COSY and NOSY, HMQC as an example. So these are the 2 examples we'll be looking at, right? Know what these name means. For example, we can just say, what does a COSY spectroscopy mean? And you should be able to know, first of all, it is a type of NMR spectrum, and it is a 2D NMR spectrum that uses 2 different NMR spectrum coupled together. Like if we look at COSY, what we do is you put the proton NMR on both your x-axis and on your y-axis. So in our previous analysis, we only look at our proton NMR on the x-axis. So that's why previously all our proton NMR analysis are one-dimensional. Now in the COSY analysis, we're putting the NMR spectroscopy on both axes, and look at how these peaks correlate with each other. Now you have the diagonal peaks, but then you have 1, 2, and 3. Those peaks are telling you information about how your protons are coupled with the neighbor of that proton. So it's telling you more information, more structural information than just one-dimensional NMR spectroscopy. And chances are we also have another type of 2D spectrum, which is called HMQC. So HMQC is heteroatom that's coupled together with your hydrogen atom. So in this case, you can imagine you have your proton NMR coupled by your carbon NMR. So you have the proton NMR on one of the axes, you have the carbon NMR on the other of the axis. Now, in looking at the HMQC, you can get information about whether or not these hydrogens are binded to that specific carbon atom. Can be very useful in solving molecular structures as well. Okay, any questions on carbon NMR before we move on? Yes?
I just had a general question. Can you just go over coupling one more time for the, like what that means? Yeah, for carbon.
So for carbon, well, there are two different things when we're talking about coupling. The first thing we mentioned coupling is when we're talking about the splitting pattern, right? So if you remember in the proton case, when you have a neighboring hydrogen, that neighboring hydrogen can create a mini plus or a mini minus and causing a mini shift on your targeted proton NMR, right? And if you have one, if you only have one neighbor, it can be plus and minus, so that's just plus or minus, either upfield or downfield. So that's a doublet. For the carbon NMR, the coupling is the same idea. We're talking about that signal, the carbon NMR signal is being affected by its neighboring atoms. But it's complicated. It's complicated because not only you have carbon-13 around that atom to create the coupling pattern or the splitting pattern, you also have the hydrogen atom around it to couple with that peak. So that's one of the things we're talking about when we're saying coupling. So that's the first time we mentioned coupling. Now, unfortunately, when we're talking about 2D NMR, we use the term coupling again. But here we're talking about a different kind of coupling. Now, when we're talking about coupling in the 2D NMR, what we're saying is how do these spectrum work along with each other? How do they correlate with each other? Maybe I should use correlate for our 2D NMR. It's how does your peak in your proton NMR correlate with that same peak, well, not the same peak, with that same molecule on the 2D NMR? Or how does your proton NMR peak correlate with your carbon NMR peak? So these two are two different concepts we discussed. Okay, well, we have about 5 minutes. Let me just get started with one of our spectroscopy problems. I highly suggest you practice it yourself without looking at the answer key. Because these kind of questions, it can be really easy when you know the answer and you look at the spectrum, you'll be like, oh, it makes sense. But when you're working that spectroscopy out, it can be super challenging. Now, when we're talking about structure determination using mixed spectroscopy, typically we'll give you information in the mass spectrum. It can be I just list it, or it can be I give you the diagram. It depends. Now, in the mass spectrum, again, what we're getting information about are the information about molecular mass. Like, for example, in this case, if I'm telling you the molecular iron has, well, 3 peaks, 284, 286, and 288. So that should be an instantaneously hit to you. It's a molecular iron, but it has 3 peaks. It's telling me that my molecule has some stable isotopes contribute to it. Either it's chlorine or bromine, and I'm giving you that information in the hit. And then at the same time, we're telling you the MZ, or the molecular mass, of your fragmented iron. So that's the base peak. It means it must be a relatively stable carbocation. Either it's a tertiary carbocation, allyl carbocation, or a benzylic carbocation that's relatively stable. So from mass spectroscopy, you can get those fragmented information, right? You know your molecule has bromine. And you know by dissociation of the bromine, you're getting your base peak. And then you look at the IR, you look at your iconic peak. Now, in this case, if we're looking at the IR, we get the idea about, okay, we don't have OH, and we do not have a carbonyl group. All right, you can get a little bit more information if you dig into that fingerprint region, but it doesn't worth too much of your effort digging to those each peak. Remember, in IR, we're not gonna necessarily assign every peak to your molecule. And then we look at our carbon NMR and our proton NMR. So for the carbon NMR, you can count it. This one is not very obvious. I'm just telling you. That's why I'm telling you it's having 5 peaks. And once you derive out your molecular formula, you can get an idea about how many carbon atoms are there, how many hydrogen atoms are there. And by knowing the number of carbon atoms and by counting the number of peaks in your carbon NMR, you get an idea about whether or not we have a plane of symmetry. And then you dig into your proton NMR and try to derive information. Now you know the splitting pattern, you know the integration, and also the chemical shift. I'll give you information like whenever it's needed. Like in this case, I'm telling you if you have a naphthalene, then your proton in the internal are more deshielded comparing to the proton on the external. It might be helpful. So just think about it and practice a little bit and check it with the answer key. Like, if you don't know how to do it, you can look at our answer key once. We're also going to do that together in our next lecture. Just do that with me once, and then do more practice until you're familiar with it. And again, I'll be hosting office hour today from 3 p.m. to 5 p.m., and feel free to stop by my office.